right. So, we'll kind of start out today. We'll revisit a little bit of discussion on bias, and then I'll kind of talk a little bit about distributions of sample means and sample proportions, kind of linking it up to things we've done Monday and Wednesday this week. So, don't think there's anything else. Oh, I had an announcement up about office hours changed on Wednesday, and I used it for every class that I had, and I didn't realize I referenced an exam that I have in a completely different class. So if any of you read that and got confused, I apologize for that. Our exam is well after spring break. I wanted to get out and announce it real quick because my office hours changed pretty unexpectedly on Wednesday. So we talked on Monday about that we only can see our sample, and we want that sample to be pretty reflective of the population as a whole. We're going to use our sample statistics to make inferences about the population. And so we want to think about different biases that can exist, right? So we'll start out with this kind of example, which is the 1936 presidential election. Alf Landon was the Republican candidate. Ended up losing to FDR, like we already know the result. But at the time, there was this literally digest. My grandma got this still when I was this young. But they did this poll, right? And they wanted to try to put out in their little like magazine booklet thing who was going to win the upcoming election. Right? So they wanted to predict the election before it occurred. They sent out 10 million mailers, right? Which I don't know what the population was back then, but it's, you know, even today, that would be a pretty good sample size. Right? So they got 2.5 million back, which, excuse me, if you're ever looking at like survey responses, 25% response rate would be really good. So they were pretty excited about this. They think, okay, we're going to predict the election. We got a pretty big sample, and they predicted a 57% landslide, 370 and 161 electoral vote win for Alf Landon. What actually happened? Well, we know that FDR won, but not only did he win, he won in a landslide in the opposite direction. I'm not a historian, but I have to imagine 523 electoral votes has got to rank up there as one of the most ever, right? So how did they get this so wrong? Right? What biases might have existed in their sample of 2.5 million people? Now I have some stupid things here. You know, did they make math errors, use the wrong formula? Obviously, that's not what went on. But what if they were more likely to have sent mailers to Republicans? So let's say they just sent all 10 million mailers to registered Republicans. Well, then they're definitely going to get a response in their sample that doesn't match up with the population. Right? So we would call that a selection bias. Right? They over-selected from one group, or they over-selected Republicans. What if Republicans were just more likely to respond? So if for whatever reason, even if they sent 5 million mailers to Republicans, 5 million mailers to registered Democrats, if 2.5 million of the 5 million Republicans responded, but 0 of the 5 million Democrat, well, now I've got a bias in my sample as well. We would call that a non-response bias. One of the groups was not responding, okay? Or they responded at different rates. So these are kind of our main two biases that we want to think about. And a lot of the times there's ways we can shut these down. And so we'll kind of mention those along the way with different examples that we use, right? But the selection bias is the idea that I'm somehow over-selecting from some group, right? Non-response bias is that some group is more or less likely to respond than others, okay? So let's go back to this example and think about how might have they had a selection and non-response bias. Okay? So what they did was to send these survey cards out. They got a list of names from this database that was created by cross-referencing telephone books and car registration. So the only way that names ended up in this database was if the person had a registered automobile and they had a name in the phone book. So who owned cars and telephones in 1936? Pretty wealthy people, people on the right side of the income distribution, right? If we look at data, people on the right side of the income distribution, people who are a little more wealthy, tend to lean or tend to vote a little bit more right or Republican. Now, not everybody, but on average, right? If we're comparing kind of lower class to kind of upper class. Right? So by using this process, we're going to end up with wealthier individuals in this data set who are more likely to vote for the Republican candidate of Alf Landon. So we had kind of this selection bias built in. So what there's some researchers that, I forget what year exactly, I think last class I said it was late 80s, early 90s. I forget exactly when they did it, but they looked at this and said, okay, how is this poll so wrong? They went and found, I think it was about 2,300 people who were alive and able to vote in the 1936 election and asked them these questions like in the late 80s, right? So they asked the people what their car telephone ownership was in 1936, and then who was the candidate that they actually voted for. So notice for people who had both a car and telephone, they found that about 53% of them actually did end up voting for Landon, right? So yeah, the poll predicted 57%, which is a little bit off, but it still would have been correct, right? It still would have been a correct prediction for the voting behaviors of people who owned a car and telephone, right? However, if they just would have used a database that didn't cross-reference, but just put anybody in who had either a car or telephone, notice people who only owned a car, about 60% of them ended up voting for Roosevelt. People who only owned a telephone, 62, right around 60%. And the people who had neither, so these we can think about probably more likely to be people who are on the lower end or the left side of the income distribution, 73% of them ended up voting for Roosevelt, right? So because we were only getting people in our survey from this group, we automatically had a selection bias built in to be more likely to predict that Landon would win. Is there something else I want to say? Oh, and you kind of also think about not only does income play a role here from their selection process, but at the time, there was more likely to be telephone lines in larger cities, rural areas, probably either didn't have phone lines or they were on, what would they call them? They weren't group phone lines, but they used to have like multiple homes on the same line. And so not only are you thinking about these are people who are tend to be wealthier, but they're also probably more likely to be from a larger city, right? So yeah, this is a kind of a nice like after the fact look and seeing what selection bias can kind of do. Okay. Any questions up to this point? Shouldn't be too crazy. So what about a non-response bias, right? What if people who are Republican were just more likely to respond? Okay. So they looked at this as well. So these 2,300 people, they kind of, I think, limited it to smaller sizes because I think if I remember right, before they contacted them, they sent them some type of a mailer or something to respond to. So they could get an idea about, well, what was the response behavior of these different people in these different categories. So, excuse me, people who, and then after they sent the mailer, then that's when they actually went and got them to be part of their survey, asked them who they actually voted for in the 1936 election, their car and telephone ownership. So what they found was people who had a car and telephone in 1936, when they sent these mailers to them in, whatever the late 80s or whatever year it was, that, before I do that, sorry, that 35% of the people who ended up voting for Landon responded to this poll they sent them, while only 17% of people who voted for Roosevelt in 1936 responded in the late 80s to this additional poll. So even for this group, right, that they were over selecting from, they also had a non-response bias. The people who voted for Landon were almost twice as likely to just return some political poll, right? So they also have this non-response bias built in, which is that they don't have people who ended up voting for Roosevelt responding as high of a percent to these different surveys. And it wouldn't have mattered here. So this is kind of a sad, I guess, I don't know. There's no real resolution to this, but sometimes when you have these non-response biases, it doesn't matter if you selected correctly. So even if they would have used just car owners, just telephone owners, if they would have been able to get people from all these groups, notice for every single group, the response was higher from people who ended up voting for Landon. So the paper goes, there are some papers about this, and it goes into maybe the reasons why. So we think about people who are wealthier, or people may tend to be a little bit more politically involved, and so they're not as likely to respond if they're on the lower end of the income distribution. But for whatever reason, it looks like that the Republican candidate voters were just a little bit more likely to respond. So it's hard to get rid of those non-responsive. I mean, it's hard to force somebody to respond to you, right? We can do things like create incentives, right? So the example I always use is I get these emails all the time about different surveys. Fill out this survey and enter to win $100 gift cards, right? So they try to create incentives to make sure that everybody has the same reason to respond, right? But you know, it's impossible to completely shut it down. We'll look at a couple other examples and think about that as well. Right? So they had a huge selection bias built in, and it looks like they also had a non-response bias built in towards Landon, and both of them kind of more likely to have people in their sample that were going to vote for Landon. And so that's why they got the prediction so wrong. Right? So what else can go wrong? So a couple of things before we go into the next couple of examples. People can just lie to you. So either maliciously or non-maliciously. So the idea of like maliciously lying to you is that if we look at drug use data, like nobody, I mean, if you look at drug use survey data, you'd think nobody is using like any illegal drug, right? But we know that there's quite a bit going on. And so people may maliciously lie to you about things, but they also may non-maliciously lie. Like if you ask somebody, you know, what their total income or what their total earnings were from the prior year, and unless it's around tax season, you're more likely to get values that are like 52,000. Well, you didn't make exactly 52,000. You made $51,159, right? But people tend to just kind of round to certain numbers, so they're not really giving you a truly accurate data point, right? Now, they're not maliciously lying. It's just a byproduct of responding to questions. Right? So we might want to think about that's going on. Also, more recently, there's been a lot of research of like just how you phrase questions. So first of all, we want to make sure people understand the question, but there's a lot of like framing, they call it. So Fox News did this thing before the last election, and I should probably try to find it, but they asked this question about trying to get at how people thought President Trump was doing. And I don't remember why. I don't think they didn't do this on purpose. So they had it one way where it kind of said something positive that he had done and then asked how people thought he was doing. They had another one where it referenced something that was kind of a negative thing and then asked people. And just by preceding the question with either a positive statement or a negative statement led to like an 8 or 9% point difference in how people kind of either favorably or unfavorably viewed Donald Trump. Right? So just the way that you phrase the question can matter. Right? So let's think about two examples. So if I were to do this, usually I use iClickers, we do the kind of an online quiz, but kind of where we're at, I'm just going to kind of think about it as though I had put this question on an online quiz and we looked at the responses. Okay. So let's say I asked all of you kind of what your health was from 1 to 4. Right? And then I collected all these online quizzes and kind of looked at the means and you know, we looked at the data. So what are some biases that might exist if that's how I did my survey? Well, for one, I tried to do a good job if I put it as an online quiz to put points to it, give an incentive to hopefully shut down some of that non-response bias. But if I didn't do that, like if I just asked you, you know, this isn't for any credit, just if you want to, please go fill this out. What people, once they look at this question, what type of people might be more likely to not respond? So think about someone in good health versus in poor health. Which of those people do you think are more likely to just not respond to this survey? Yeah, probably, right? Like if I'm in good health, why do I care if someone, you know, that's actually, I probably want people to know it. Whereas if I'm in bad health, maybe I don't want that kind of information to be put out there. And so whenever we ask people like questions about their health, anytime it's like a negative, or even if it's not about health, if it's about, you know, time use or anything like that, if their behavior, if they believe it's going to be viewed negatively, they might be more likely to just not respond, right? So we might always end up with a slightly inflated value because we're getting more people in our sample who are better health. So there might be some non-response bias there. What's the selection bias if I was asking you guys about your health and I'm thinking about the health of the US population? You're all pretty young. So what do you think is true about your health relative to an 80-year-old? It's probably a little bit better, right? If I have a younger population in my sample than younger individuals in my sample than the population as a whole, well, then I'm going to have a bias in my health measure, right? So we could think about a selection and non-response bias. And a question like this, maybe people maliciously lie, right? Maybe if they think they're in poor health, they just overinflate how healthy they feel because they think it'll be recorded if their name's attached to it. So you might get some lying there. You're also going to get some non-malicious lying, right? Two forms of that. One is that when you look at data, so there's been a couple studies where they measure different, I don't know, heart rates, blood pressure. And when you look at actual metrics of health, and then you ask people how they view their health, they always have a negative view of their own health. People are generally healthier than they actually think that they are, right? So, but they're not trying to lie. It's just for whatever reason, there's something built in us that's how people respond, right? Maybe a psychology thing. Also, if I give you just 1 through 4, well, what if I feel like a 1.5? I can't say that, right? So by making it discrete, by giving people only a small set of options, you're almost forcing them to really non-maliciously lie to you. Now, how different is a 1 from 1.5? I don't know. That's a different, that's a different discussion. But if they feel like a 1.5 and these are their only responses, they're going to have to give you a response that's not completely accurate. Right? So we have all these different biases that might occur. One could also be the just interpretation of the question, right? I did say that 1 was the best and 4 was poor, but maybe someone reads this quick and says, oh, 1 to 4, I feel really, really healthy. 4 is the highest. So they respond with a 4 real quick when 1 was actually the best, right? So maybe you get kind of a misinterpretation of the question, which is why something like this would be really important to make sure that it's very clear, right? Because if they misunderstand the question where they think 1 is the worst, you're going to literally get the exact opposite of response of what someone actually feels. Right? So it's just some examples where we can be aware and conscious of these different biases that might exist. Okay. What if I was asked like the second one? So what if I asked how many alcoholic drinks on average you have every week? And I give you these 4 categories. Right? So what's a non-response bias that might exist here? Who might be more likely to not respond to this? Maybe people who are drinking a lot, right? Maybe they don't want that to be known, and so maybe they just don't respond to this survey. Right? Maybe people who are under 21 don't want to respond to a survey where they think their name's going to be attached to this or something, right? And so that might kind of it might kind of decrease the mean that I'm seeing from my sample. If I'm getting these people who are drinking a lot and they're just more likely not to respond, well, then my sample ends up with people whose drinking behaviors are a little bit less. Right? What's maybe a selection bias I would have if this is a question I asked like on the online quiz? So you guys are college students. What do you think is probably true about your drinking behaviors relative to the population? It's a little bit higher. I'll let you know. I hang around people even my age. They don't drink like the people I knew in college, right? So we might have a selection bias there if I've got a younger group in my sample than the population as a whole, right? So selection non-response bias could exist. Maybe we get people that are maliciously lying, right? Maybe people are underreporting. They're just telling you 0 because they are under 21. So even if they respond, they're telling you 0 because they're not 21 yet. Maybe you get, that one guy at the party always wants to tell you that he drinks, X number of beers, so maybe you get people over inflating how much they're drinking, right? So you might have some lying going on, maybe some non-malicious lying. Maybe people don't keep track of exactly how many drinks. And so they just they give you a response of what they think is right, but maybe it's technically they should be, in this category, right? So you have all these biases that could exist. And they're just things that we want to be aware of, especially when we're thinking about data that was collected from surveys, right? And this will come back up again once we get to linear regression. We'll talk a lot more about biases that exist in our collection. For now, we just want to be aware that they exist. Right? So I think an interesting kind of example of this, and we kind of already did a political one, but this one's a little bit more relevant, or sorry, shouldn't say relevant, recent. And I kind of tried to build this off of 2 papers that were put out. I know the one was 2018. I forget when the other one came out, but they were looking at the 2016 election, and they were like, man, there was like one major polling company, or what you call it, that actually got it right. And like almost all of the polls prior to the 2016 election had Clinton winning, right? At the very least by a pretty significant margin, some of them, the popular vote. And how'd they all get it wrong? Like, what was it? What biases might have been built in to their survey methods, right? So why did they all get this wrong? So let's think about some different biases that could exist. So what might be a selection bias that exists when we look at political polling? So especially when we go back in time, not so as much for the 2016 election, but any surveys that are still being done kind of face-to-face or maybe making phone calls. Well, in larger cities, you just have a larger mass of people. And so it's very easy to get a large number of people into your sample, right? So if people, if only 10% of people that you stop are going to actually respond to you, well, it's a lot better to be in New York City than it would be, Muncie, Indiana, right? Because you can get a lot more people, even if the rate is relatively low, right? So if they're located in these larger cities, that's where they're doing more of this polling. Potentially, right? We know that people that are urban versus rural tend to be a little bit more left-leaning, right? So maybe they had a little bit of a selection bias built into some of their polls if they were over-selecting people from larger cities, right? Some of it, the paper also gives, well, but maybe, if we're not doing this, face-to-face, if we're doing some type of phone calls or we're doing something online, it might be that, if we looked at people who are more likely to be involved in politics or to respond to a survey that they see online, tend to be that people on the right are a little bit more likely to kind of respond to this. We saw that in the 1936 data as well. So maybe I've got some type of a selection bias going on there. But we can think about also what non-response bias might exist. So one thing in the 2016 election that this paper really goes into depth into is anytime you're doing polling, it's an issue if there's a social cost to responding with a certain candidate's name, right? So I would, I don't think I'm going out on a limb here to say, a somewhat divisive character is Donald Trump, right? And especially in the 2016 election, I think there was definitely somewhat of a social cost to people who would have said they were going to vote for him, right? And so maybe instead of responding, they just didn't respond to any of these surveys, right? They got a phone call. Well, I don't want to go through this. I don't want this person, maybe if I feel like they're going to view me negatively, I just don't want to go through that. So just don't respond, right? So we might have had this kind of non-response bias built in. And the kind of paper goes into like, this is Trumpers they call them Trumpers who are staying quiet, right? So we might have had a little bit of that built in, which is more likely to give us Democrats in our surveys or in our polls. And so it was more likely that we predicted that Clinton was going to win, right? So we had a little bit of selection bias and non-response bias built in for predicting that the Democratic candidate was going to win, Hillary Clinton. So another thing they go into was, at the time, these weren't like the two most loved candidates. And so a lot of people maybe just hadn't made their mind up when they were being polled. And so if you have a social cost to saying that you're going to vote for Donald Trump and you're not really sure who you want to vote for, well, just say the other candidate. If someone's just asking for a political poll, what do you care, right? And so there might have been a lot of like unintended lying, people who hadn't made their mind up yet. Because there's a social stigma or a social cost to saying one candidate, we just respond with the other, okay? So maybe we had some unintended lying that also built in this bias towards thinking that Hillary Clinton was going to win when we look at these samples. And then kind of the last one, which is malicious lying. The paper called these shy Trumpers, which was the idea that some people knew they were going to vote for Trump, but when asked about it, because there was a social cost, a social stigma to it, they just responded with they were undecided that they were going to vote for Clinton, right? So this paper tries to highlight that, if we're just trying to predict polls, we want to make sure that when we're collecting data, that there isn't some type of social stigma or social cost associated with any response for either candidate. Now, how can you shut this down? Well, you can't change, what's going around on Twitter or what's going on in your entire society. But what you can do is try to create more anonymity, right? You can do less face-to-face contact. So probably the polls that are most likely to be accurate when you have issues like this going on are things that are done online, right? Where there's no face attached to it. They're responding to a computer, so they don't feel or they don't think about this social stigma or the social cost as much, right? Which I think the one, was it Reuters that got the 2016, right? I think predominantly a lot of their data, it's all collected online, right? And so maybe that's why they were one of the ones that were a little bit closer to be able to correctly predict the election. But kind of an interesting kind of case study almost this paper goes into. I'm sure someone will try to collect data kind of like that paper did for the 1936 election at some point and really try to put some actual numbers to what the selection and non-response bias actually was. Any questions up to this point? Just kind of going through this, usually somewhat of a fun discussion or a little easier to think about, right? So we've got these biases that we think exist. We want to be concerned with them, or at least aware of them. And I threw some additional slides in here, but I'll post these up on Canvas. I'll just repost the lecture 8 with these additional slides at the end. And I want to point something out before we go into this. So we tried to relate the first part of the discussion is kind of more towards like what we were doing Monday. We talked a little bit about cluster random sampling. Now I'm going to try to relate a little bit more to what we did last class. So we were thinking about our distribution of our sample means. So I want to try to make a point here in thinking about how the sample size influences our distribution. So we said as long as we get a sample size over 30, our sample mean distribution will be normally distributed. And it should be normally distributed around whatever our population mean was. We then said the variance of our sample mean was the variance of the original data over our sample size. Okay. That was kind of the setup that we had. So let's think about how do I want to set this up. I might not have left myself enough room. No, this is okay. I'll do the best I can here. So let's say I want to know what's the probability I see a sample mean in between these two values. And maybe these values correspond to something like 1 standard deviation above and below the population mean. But whatever they are, like you can kind of see I've set it up so that it's values that are close to the mean. Right? So I could turn these into z-scores, just kind of going through the process of last class. I turn both of these values into a z-score. All right, look up this z-score, find the area to the left, look at this one, find the area to the left, subtract the smaller from the larger one, and then be left with what's in between. Right? That's kind of what we did last class. But let's think about what happens. So I come up with, and I can put a probability to this. Like maybe I look these up, when I subtract them, I end up finding, I don't know, the probability of seeing something in between A and B here is 0.2. It's not really important, just putting a number to kind of give us an example. Well, let's assume that when we went through that process, that was for a sample of size 50. But then I go out and I say, well, I can do better than that. And I'm going to get a larger sample of size 100. Well, what does that do to the distribution of my sample means? Well, it doesn't matter what my sample size is. They'll still be centered around whatever that true population mean was. However, if my sample size is larger, what happens to the variance of my sample means? It's going to go down. Right? So if I have a lower variance, it means that the data, right, varies less from that mean. So more of the observations are going to be centered right around the mean, less likely I see values further from the mean. Right? So this lower variance, that distribution might look something like this. Not a perfect at drawing this, but something like that, right? A little bit more peaked. Well, now if I think about what's the probability I'm in between A and B, right? Well, I can kind of see here, it's going to be a little bit more, right? So instead of 0.2, now maybe I get that there's a 0.3 probability I see something within this range. Right? So because that probability is increased, what I'm really saying there is, if I take a higher sample size, it's more likely that I see something in this range of values that is close to the mean. And I could almost think about it if I chose a value out here. Well, notice with a sample size of 50, here's the probability I see something that's this far away from the mean. With a sample size of 100, the probably I see something that far away from the mean becomes much, much smaller, right? So by taking higher sample sizes, I can increase the probability that I see a sample mean that's closer to the true population mean, which is good because in practice, I can't see this. In practice, I only get one sample mean, so I want to guarantee, I want to have a higher probability that it's going to be a value that's close to that true population mean, because I'm going to be using that sample mean to make inferences about the population. So that's kind of the importance of getting a higher sample size. And actually, once we come back from spring break, like going through confidence intervals and hypothesis testing, we'll see like higher sample sizes are always good. Higher sample sizes are almost always a better thing. So that allows us to guarantee that the sample statistic we see is more likely to be close to that population value. Okay. We're getting time here. I'll make another point. Let's think about this. If I were to turn these values into z-scores, remember z-scores tell me how many standard deviations away I am from that population mean. So if I keep using the same two cutoff values, these are going to be, so I turn these into z values. When I have a higher sample size, that's going to decrease my standard deviation. So these values will actually end up being a higher number of standard deviations away, right? So these z values will actually get a little bit larger, right? So I can think about not only does having a higher sample size influence my variance of my sample means, but because my z-score is how many standard deviations away I am, well, that's also going to change the z-scores that I come up with as well. Okay? If the standard deviation is smaller, the same value is going to be more standard deviations away from the mean. Okay? Any questions on that before we keep moving here? All right, so I think I'm gonna, actually, I put those slides in there, but I think I can do a better thing by just drawing it for you. So we'll have our reference up here. So there are a distribution of our sample means over sample size over 30, normally distributed. The mean of my sample means was the population mean. Variance of my sample means was the variance of the data I sampled from over my sample size. We said when we calculate z-scores for a sample mean, this was where we took the cutoff value we were interested in, subtract the mean of my sample means, divide by the standard deviation of my sample means, which the mean of my sample means just is the true population mean, and the standard deviation would be the square root of the variance of my sample means. So this is what we did last class. If I think about my sample proportion, now a proportion we can think of as just like the number of successes over number of trials. So it's starting to sound kind of like a binomial, right? The number of successes, well, that's what the binomial distribution told me, right? The number of trials here is going to be the number of times that I'm looking at them. So this could be as simple as if I'm asking people who they're going to vote for, the number of people who respond with candidate A divided by the total number of people I asked. So you kind of think about the number of trials here is just going to be N, my sample size. The number of successes, well, we're thinking about the average number of successes. Our binomial equation for the mean, or our average number of successes, was just N times P. So we're thinking about, and sorry, I should have said our sample proportion here. I'm thinking about my sample proportions, right? They should be centered around whatever that true population proportion is. If I can find the average number of successes, then the average proportion of successes will just be whatever that population proportion is. So now when I'm thinking about the distribution here of sample proportions, now sample proportions, right, if I'm looking at the number of successes out of the number of trials, has to be between 0 and 1, right? But between those values, it should be, if we get a sample size over 100, normally distributed. The mean of our sample proportions should be centered around, just like the sample mean distribution was centered around the true mean. the sample proportion distribution should be centered around the true population proportion. Okay. You think about it this way, if I flip a coin 100 times and I write down the proportion of times it came up heads, maybe the first time I flip it 100 times, I see 51 come up heads, so 0.51. And the next 100 coin flips, I see 0.48, and then 0.43 or 0.54. But I'm seeing kind of values that are really close. They're all going to be centered right around that true population proportion of flipping a coin, which should just be 0.5. Right? So should be centered around that true population proportion. The variance of my sample proportions. Well, remember the equation we had for the variance. Actually here, I want to hold off on this. Sorry, the variance of my population proportion. Well, we had the variance equation for our binomial on the number of successes was n times p times 1 minus p. But if we're not looking at the number of successes now, we're looking at the proportion of successes. So we will divide by the number or sample size, the number of trials. So notice the variance of our proportion is just p times 1 minus p, which then means the variance of my sample proportions. Well, I'll get this on the same thing. So remember, the variance of our sample mean was the variance of the data we sampled from divided by our sample size. Variance of our sample proportion will take the variance of that, like kind of like the data we sampled from here, but it's going to be from the true population proportion. So p times 1 minus p really is our variance, right? So you can think of it here. This was like the variance of our variable x. Here we've got the variance of our proportion p. And then similarly, we divide by our sample size. Okay. Everybody with me up to this point. Okay, so the next point that I want to make is now that we have this, I'm going to try to keep this right here. There we go. How could I come up with a z-score for my sample proportion? I'm going to follow the exact same procedure I did for the sample mean. So I take whatever statistic I'm looking at. Here now I'm looking at my sample proportion. And that might be, some cutoff here, right? And I want to find the probability I see a sample proportion this low. I'll then subtract the mean of the statistic I'm looking at and divide by the standard deviation of the statistic I'm looking at. Well, the mean of my sample proportions is just the population proportion. And the standard deviation of my sample proportions would just be the square root of p times 1 minus p over my sample size. Okay. So notice that z-score equation follows the same process we were doing before. It's just now it's specific to the statistic we're interested in. And to calculate the standard deviation, we're gonna have a slightly different method there. But once we have that z-score, once I turn this value into z-score, I can look that up in the table, find the probability I see that or anything below it. It's going to be the same steps as what we were doing before. Okay. So once we get that z-score, which slightly different equation for proportions compared to sample means, but once we get that z-score, the whole process is exactly the same. Right? So I think here I've kind of got what we just laid out, and then thinking about how do I come up with that z-score. So like I said, I'll repost the slide so you have all this as well. But then we could think about an example, right? So what's the probability if I flip a coin? What's the probability it comes up heads 55 or more times? Right? So we think about if I've got my sample proportions, my sample size is 100. So it's definitely going to be normally distributed. It should be centered around that true population proportion, which if I'm flipping a coin, what's the true population proportion? Just 0.5. And I'm interested in the sample proportion cutoff value of 55 or more heads. Well, 55 heads or more out of 100, 0.55. So there's that sample proportion value I'm interested in, and I want to find the probability of being greater than that. Okay. So I'm going to turn this into a z-value. that value of 0.55 is going to have a certain Z value. I can look it up in the table. The table will tell me the area to the left. I wanted the area to the right, so I'll then need to subtract it from 1. Okay. So how do I find that Z-score? Right? Well, we said take your cutoff value, subtract that population proportion, divide by the square root of the population proportion times 1 minus over n. Remember, this denominator just represented our standard deviation. So the sample proportion value I wanted was 0.55. The true population proportion was 0.5. And then 0.5 times 1 minus 0.5 divided by our sample size of 100. And I think you'll get that Z value of 1. Okay. So slightly different equation, right? But a pretty similar setup with what we were doing with sample mean. So once I've got this Z value, from here, it's the same as what we've been doing, right? So I can go, to my table, look up that Z value of 1.00, 0.8413. That's going to be my area to the left. I wanted the area to the right, so I'll subtract that from 1. Get what, 0.1587. So once I get the Z-score, all the steps are exactly the same. And that Z-score really follows a very similar, really follows the same kind of method as what we were doing with our sample mean. It's just that when we calculate the standard deviation of the statistic we're interested in, it's going to be a little bit different than if that statistic was a sample mean, right, relative to a sample proportion. Any questions there? So I think when I post these slides, I have another example at the end here, very similar to what we just did. But if you want one to kind of work through on your own, that might be a good one to look at. Other than that, so you've got that Connect and Excel assignment. So hopefully you've kind of made some headway on those. We should be able to get pretty much like through those entirely now. Through the Connect entirely. The Excel, we'll kind of get through part of it, and then we'll cover the rest of it that first week back from spring break, which is when we'll do confidence intervals. So confidence intervals are going to kind of set us up to thinking about really everything we're going to do for the rest of the semester, or at the very least, especially directly related to what we're going to do up into the next exam. So everybody come back Monday, kind of ready to go. We need to get a really good base understanding of confidence intervals to set us up for success kind of moving forward, okay? I think other than that, there's no more questions for me. All right, so have a fun, safe spring break. When we come back, we can all see what each other looks like. We're not going to wear masks anymore, so this is great news, right?